Automated decision-making processes now dictate everything from global logistics to individual credit scores, yet the mechanics driving these systems remain widely misunderstood. Artificial intelligence serves as the broad, overarching umbrella. It encompasses any system designed to mimic human reasoning and logic across both structured and unstructured datasets. Machine learning is a specialized application within that space. It uses statistical algorithms to learn autonomously and produce predictive models. In traditional programming, an engineer feeds input data and a pre-written program into a machine to generate an output. Machine learning inverts this flow. The engineer feeds the input data and expected output into the machine, requiring the computer to derive the programmatic rules itself. A system technically learns when its performance on a specific task improves through experience, as measured by a defined performance metric. This shift from human-written instructions to machine-derived logic dictates the entire architecture of modern computational systems. The theoretical roots of the field reach back to 1943, when Warren McCulloch and Walter Pitts designed the first neural network models using electrical circuits. By 1950, Alan Turing had introduced the Turing test, providing a formal framework to evaluate machine intelligence. For decades, progress was restricted by the limited volume of information humans could manually digitize and input into these early systems. This timeline shows how the trajectory of the field altered in the 1990s. The sudden availability of massive data volumes transitioned machine learning into a purely data-driven discipline. This influx of information led to significant breakthroughs, such as IBM's Deep Blue defeating a world chess champion in 1997. Modern machine learning was realized by feeding foundational algorithms the immense volume of data they required to compute their own internal rules. Traditional machine learning models operate on a two-channel architecture, separating the training data collection from the active prediction phase. This reliance on static training sets makes these models slow to adapt. Once the training phase is complete, the model's logic becomes fixed. If the environment changes, even minor alterations to the input data will disrupt the model's precision and cause the output to fail. This failure mode is known as concept drift, where shifting real-world variables render a static model's recommendations outdated. Adaptive machine learning addresses this by operating on a single-channel system that processes data in real time. By learning from its own past mistakes, the adaptive system continually updates its predictive logic without relying on obsolete historical data. Maintaining accuracy in fluctuating environments requires a transition to these single-channel, continually updating architectures. An algorithm's learning category is defined strictly by the state of the data fed into the system. Supervised learning requires a curated dataset where every point is manually labeled by human engineers. The algorithm maps specific inputs to categorical outcomes, like spam filtering, or continuous outcomes, like market trend regression. Unsupervised learning operates on raw, untagged data, providing the machine with no predefined answers or labels. The algorithm autonomously analyzes data to discover hidden structures. In clustering, the model groups similar objects together without being told what they represent. Association models identify relational dependencies between variables, like connecting viewer behaviors on a streaming platform. Autonomous vehicles use these methods to detect and track obstacles in real time, grouping shapes based on motion and proximity. These models operate at high speeds because they bypass the need to check inputs against a static dictionary of human-provided labels. While human supervision maps known inputs to outputs, unsupervised architectures excel at identifying mathematical patterns invisible to the human eye. The high cost of labeling massive datasets often makes full supervision impractical, leading to the use of semi-supervised learning. These models use a small amount of labeled data to infer the structure of a much larger unlabeled set, optimizing both cost and accuracy. Reinforcement learning shifts away from datasets entirely, relying instead on direct environmental feedback. An agent navigates through trial and error, with its internal logic designed to maximize its cumulative reward over time. This feedback-based process allows algorithms to solve multi-step problems, such as mastering the complexities of the board game Go. Because the agent generates its own experience through live iterations, it does not require a historical record to begin learning. The four categories of machine learning represent different structural responses to the specific type of data available to the system. These models are strictly bounded by mathematical limits, and their performance is only as reliable as the data used to build them. Non-representative or biased training data will skew analytical results, regardless of how sophisticated the algorithm itself may be. Underfitting occurs when a model is too simple to capture the underlying trend of a dataset, as seen in this graph where a straight line fails to account for a clear curve. This creates a model that is too rudimentary to be useful in practical applications. Overfitting is the opposite failure mode. Here, the model has memorized the specific noise and outliers of its training data. This results in a system that performs perfectly on its training set, but fails to make accurate predictions when faced with new, unseen data. Successful engineering requires a constant balance between model complexity and the purity of the training data. Machine learning is the autonomous statistical mapping of inputs to expected outputs. This mapping now facilitates life-saving medical diagnoses, from building 3D tumor models to predicting genetic diseases. The same logic powers the virtual assistants and utilities that operate within billions of homes every day. Every application, whether it uses labeled datasets or environmental trial and error, adheres to the core axiom of improving performance through experience. To remain effective over time, these systems must utilize adaptive architectures that continually test their own logic against current reality. As long as these architectures are fed with pure, unbiased data, machine learning will remain the primary vehicle for advancing computational decision-making.